Hi, I'm Sachin from the Faculty of Electrical Engineering, Mathematics, and Computer Science at Delft University of Technology. In this tutorial, we will briefly discuss the Laplace transform as introduced in the lecture video and explore its application through a worked example. We will start by revisiting what the Laplace transform is and why it is such a powerful tool. After that, we will examine the motor model discussed in the lecture and solve it using the standard Laplace transform techniques. Let's begin by understanding what the Laplace transform actually is. Most real systems, such as an RC circuit or a falling ball, change continuously over time. These real world phenomena are expressed mathematically as functions of time denoted by f of t. However, solving time dependent equations can become complicated, especially when multiple variables or derivatives are involved. The French mathematician Pierre Simon Laplace provided a new approach. He described these systems in terms of a new variable S, transforming the problem into a domain where the mathematics became much simpler. Here is the formal definition. It shows that the Laplace transform is an integral transform, which means it is the integral of a time domain function multiplied by an exponential term. Because this integration extends from 0 to infinity, it captures how the function behaves over all future time, providing insight into what the function can and cannot do in the long run. In practical terms, we take all possible values of f of t, multiply each by an exponential weighting factor, e raised to the power minus st, and add them up. The result, fs, describes how the system behaves in the Laplace domain or S domain. This S domain is complex, meaning that S has a real part, sigma, and an imaginary part, omega, allowing us to analyze both growth and oscillation in a unified framework. Now that we understand what the Laplace transform is, let's discuss its key advantages in more detail. When we use the Laplace transform, something remarkable happens. It converts differential equations into algebraic equations. Normally, solving a differential equation requires taking derivatives and integrals, which can be tedious. But in the Laplace domain, differentiation becomes simply multiplication by s. This means we can replace complex calculus operations with simple algebraic manipulation, multiplying or division by s. In most real world problems, we also need to account for how the system starts. These are called initial conditions. Usually, we apply them at the end of the solution to find constants. However, with the Laplace transform, these conditions are naturally included in the transformed equation. For instance, the Laplace of the second derivative of y of t is shown in equation 3. So, when we transform a differential equation, the initial values appear automatically. This saves time and avoid the messy process of solving for integration constants later. An example of this advantage can be seen in equation 4. Once we have the Laplace form of a system, we can analyze its behavior without fully solving it. For example, engineers study the poles of f of s. These determine the stability of the system. If the poles lie in the left half of the S plane, the system is stable. If they lie in the right half, the system may oscillate or become unstable. We can also understand how a system responds to various inputs, such as step or impulse signals, directly from f of s. In this way, the Laplace transform provides deep insight into system dynamics and performance. Finally, the Laplace transform is used everywhere in engineering and science. In control systems, it forms the foundation for transfer functions and feedback analysis. In circuit theory, RLC circuits are solved almost entirely in the Laplace domain. And in signal processing, filter design relies heavily on S domain techniques. Learning the Laplace transform is not just learning another mathematical trick, it is learning the language of modern engineering. It unifies time, frequency, and design in one powerful analytical framework. Now that we understand what the Laplace transform is and why it is valuable, let's move on to the worked example, the motor model from this module. Imagine we need to solve the differential equations for a motor circuit to find the relationship between the armature voltage and the rotational speed of the motor. The governing equations are shown in this slide. By substituting equation 5 into equation 4 and then that result into equation 3, we obtain a second order differential equation for the armature voltage. Solving this equation directly would require knowledge of second order differential solutions, which can be quite involved. To simplify the problem, we can use the Laplace operator to convert these differential equations into algebraic ones. Note that the initial conditions do not appear in equation 9. This is because we assume the motor starts from rest, meaning both its initial speed and acceleration are zero. After applying the Laplace transform and rearranging terms, we can express the speed in terms of the armature voltage as shown in equation 11. Before solving for speed, we must define the input signal. Here, we assume the armature voltage is a step input, which makes physical sense. The voltage is initially zero and then suddenly applied when the drive is turned on. The Laplace transform of a step input with amplitude kappa is kappa divided by S. So, moving forward, we replace VA of S with VA divided by S. The final equation to be solved is shown in equation 12. A common technique for solving such equations is partial fraction decomposition, which reduces the order of the denominator to match the standard Laplace transform solutions provided in this slide. Another useful method is the shifting property, particularly when the denominator is quadratic and does not directly correspond to a standard form. Continuing from equation 13, we rewrite the equation as shown in equation 11 so that it matches the known standard solutions. Finally, by applying the shifting property and referring to the standard Laplace tables, we obtain the complete time domain solution as displayed on this slide. In conclusion, in this tutorial, we reviewed what the Laplace transform is and why it is used. We then applied it to the motor model discussed in the lecture video and demonstrated how the Laplace transform allows us to solve differential equations more easily. This concludes the tutorial. Thank you very much for your attention and good luck with the rest of the study.